what's x to the n? What's the derivative of x to the n? N x to the n minus 1. All right? Regardless of whatever, as long as n's a rational number. If you have, this is something that we looked at before, right? If you have a derivative of a constant, like if you say a function is 3, its derivative is 0. If you have a constant times a function, here I'm using u to be, u is a function. U is just something like f or whatever. It's a function there. C times u. Constant times a function. It's a constant times whatever the derivative of that function is, right? Like if somebody says find the derivative of 5x to the 7th, what you think in your head is you think, I'm just going to ignore the 5 at first, right? If you want the derivative of this whole thing, this is kind of goofy notation doing this. Actually, let's use better notation so I don't have to say that then. If you want the derivative of that function, just ignore the 5 at first and think, what's the derivative of that function? And then multiply it. What's the derivative of x to the 7th? 7x to the 6th, and then multiply the 5 after, 35, x to the 6th. If you already have a constant in front of your function like this, just ignore it at first, and then multiply it in later. The sum and the difference rule here. Again, it's you can call it a rule if you want, but if you know what the derivative of x cubed is, what's the derivative of x cubed? 3x squared. What's the derivative of x squared? 2x. Then if you take this function and this function, if you put those together, okay, if you take this and say now, what's the derivative of if some function is called that, right? Those together, if you add those two functions, their derivative is just the sum of the two individual derivatives. So this one and this one added together. Right? The derivative of the sum of two functions is just the sum of the derivatives. Right? Derivative of a sum is the sum of the derivatives. Derivative of sum is sum of the derivatives. I don't know if words help you, but... Okay, the derivative of a sum is a sum of the derivatives. The derivative of a difference, subtracting the two, so u plus v, if you have that as a function and you want the derivative of that, it's whatever u prime is and whatever v prime is, just add it or subtract it. And then so if we have a sum and difference rule, we need a product and quotient rule. The product rule, if you have the product of two functions. Okay, well let's check this using what we just had here. I had one function was, so let's make up some specifics here. Let's say if u was x to the third and v was x squared. If I want to know now what the derivative of u times v is, so in other words, u times v is, what is u times v? It's x to the third times x squared, or x to the fifth, right? That's what u times v is. What's the derivative of x to the fifth? 5x to the fourth. What's the derivative of these two individual functions? 3x squared, 2x. Is the derivative of a product the product of the derivative? No, right? 3x squared times 2x definitely doesn't give you this, 5x to the fourth. It would be nice if it did, but it doesn't. What it actually is this. Okay, you have your list of functions here. This is where it's going to come from. It's going to come from this times this. Plus this times this. Okay? It is. You try this for any function you want. It's if you want the derivative of u times v, it's u prime times v plus u times v prime. I don't think going through and doing some formal proof of this is going to help, but I want to show you something that might help you understand the concept. If you have a function that comes from two other functions multiplied, two other things multiplied, it's like having two variables, right? So let's say you had, the simplest thing is to use the area of a rectangle. If we have a rectangle here, now I'm going to change its area. So let's say we had that its width was u and its length was v, or whatever, the two dimensions. Width, length, doesn't matter, those two dimensions. If I'm going to change it, I guess I don't actually want it. You know that one of them's u, one of them's v. It's not going to shift very nicely if I do this. If I start to change this, actually it's not going to allow me to do it both directions here, but so I have to draw it freehand, I think, for this to work. I don't know if it actually allows me to change it in two directions. I can't. Okay, well, never mind. It doesn't work too well. I have to do it in Microsoft Word. But anyways, if I was to change this one way or the other way, well, I'll have to show you this after. Okay, so this is going to work better here. If I change this, if I start to, let's make it smaller to start with here. If I start to change this, the rate that the area is going up, okay, the amount of, the derivative is the rate of change. The rate that I'm gaining area as I drag it this way is dependent on two things. If I'm dragging it really fast, I'm gaining area pretty fast. If I drag it really slow, I'm gaining area pretty slow. So it depends on how fast I'm dragging it horizontally. It also depends on how wide it was in the first place. If I drag it at this rate to the right, I'm gaining a lot of area because it's really wide, even though I'm going slow. Or if it's narrow and I drag it really fast, I'm gaining a lot of area, like I don't know how many square millimeters per second or something like that. If I drag it this way, I'm gaining area based on how fast I'm dragging it, how fast this dimension's changing, and how wide it is. All right? How wide it is and how fast I'm changing this. The rate that I'm gaining area, if this is v and this is u, the rate that I gain area is how wide it is times how fast I change the length plus the other direction, how fast I change u times how wide it is this way. If I change it both directions at once, okay, if I change it both directions at once, like if I go this way, it's how fast I'm changing it each direction times the opposite, right? When I go this way, I've got however wide it is, how wide it is times how fast I'm changing this direction. U prime times V. Plus, if I go the other way, it's how fast I'm changing this, the derivative, times how wide it is here. That's kind of a visual way of seeing why the product rule works. Come back to that as you work with this more and as we work with some kind of real problems and stuff like that. Try it out for this if you want to see. You have u prime times v, right? It's u prime v plus uv prime. Try it out here. It's 3x squared times x squared plus x cubed times 2x. What does that give me? 3x squared plus 2x, sorry, not squared, fourth. 2x to the fourth, 5x to the fourth. It's going to work for any function you pick, okay? The quotient rule is a little bit more It's actually not, I mean, you're going to have to kind of remember these things, but if you make connections between them, don't think of this one as a totally separate thing. It's actually almost like that one. Okay, except what? Minus. Well, and divided by v squared. But. So it's almost the same, except it's totally different. Well, if you have to remember, when you remember things, it's better not to remember them all as individual things, right? Remember them based on the differences. Don't remember this as a totally separate thing, right? Remember that the top part is almost the same, and oh yeah, there's this v squared on the bottom, and there's a minus. Okay? Here's what I would like you to do. There's lots of problems in here. There's no more concepts to get in this. There's no more concepts. There's you working these things out. Let me scroll through here and tell you a bit about it. Find the derivative of those. You can check because you have the answers at the back of this whole package. This is not a proof, but it's kind of a justification to show you. It's an example of showing you, first of all, do this by expanding that function like you would have in grade 9. Multiply it out to a simpler function, then find the derivative. Method 2, use the product rule. And then what am I going to hope you do at the end here when you do it those two different ways? Make sure they're the same answer, right? Make sure they're the same answer. Do it by expanding it with, multiply that out like grade 9s would do, and then find the derivative. The same thing with this, the quotient rule. Do it by actually dividing it to make two separate pieces first. X squared divided by 2x and 3 divided by 2x. And then do it by using the quotient rule. Make sure you get the same thing. And that's going to be, I guess, the falling down point for this one is going to be the grade 10 algebra, not the calculus level stuff. There's not really much to tell you other than second derivatives. Well, as soon as we start talking about the second derivative, we've just talked about the derivative, first of all. Here's a function, whatever, and here's its derivative. We used a little tick mark. The second derivative is the derivative of the derivative, right? What would the second derivative of this be? It's the derivative of the derivative. So second derivative is like 2 down the line here. This is going to be 6 times x. The third derivative is going to be derivative of 6x is just 6. You can connect this later on. We're going to connect this with, if this is a function like a position function, this is the rate of change of that position function. What's the rate of change of position called in physics? Velocity. What's the rate of change of velocity called? Acceleration, and so on, right? Up till now, we haven't talked about this being called the first derivative because you need the second thing before you call the first thing the first, right? They didn't call World War I until World War II happened, right? They called it the Great War before that. You don't call yourself like John Smith the First until there's a second, right? Queen Elizabeth I you don't call her that until there's a Queen Elizabeth II, and so on, right? So this is the second derivative, third derivative, and so on. You work through and finish those questions, and then we're at this point, and we can set a date for this. You have a good chunk of time here that you can use to do this.